Hi Math 215 students. In this video we're going to talk a bit more about matrix transformations and introduce the idea of linear transformations. Before you move on from this video, please do your best to do all the things listed here. We'll show this list again at the end of the video. But in particular, please pay attention to the definition of a linear transformation. This will be a very important concept through the rest of the semester. All right, so if we were to do a bit of review from the last video, there we defined a matrix transformation to be a vector function having the form where your function takes an input vector x and multiplies it by matrix A, where A has the right dimensions to make it work. So as our example, we looked at T of x is this matrix times x. We talked about functions. We reminded you that that's a rule for assigning a unique output for each input in there. And so if we plug in a vector for x, like 1, 1, then the function will spit out an output vector. And the fact that we got this vector by timesing 1, 1 by a matrix makes this a matrix transformation. All right, in the last video we talked about the domain of T. Remember that in order for the function to be defined, you need to have the right number of entries in X to correspond to the columns of the matrix. And we talked about how the range of this output function is some subset of R3. In this particular case, that was because there were 3 rows. So in general, if there are m rows, your range will be some subset of Rm. Okay. With that introduction, let's move on and talk about what some of these matrix transformations look like. So before we do anything else, we want to kind of understand sort of what these do in practice. And so we're going to start by looking at R2 to R2. We'll make a matrix transformation by setting T of x equal to this 2 by 2 matrix times x. So in particular, just as an example, if you were to plug in the vector 2, 0, you would take 2 times 1/2 and 0 times minus 3/2 to get 1. And then you would take 2 times square root of 3 over 2 plus 0 times 1/2 to get the square root of 3. And 1 square root of 3 is your output vector. Okay, now pictorially, this gives us a little bit of information. Because our input vector has to come from R2, we need to represent that the input vectors correspond to points in the two-dimensional plane. And since the output is also two-dimensional, we're going to, instead of doing one graph showing both the input and the output, we'll have a graph showing some input vectors and a graph showing what happens to those input vectors after the function. So for example, we saw that 2, 0 mapped to 1 square root of 3. So that 2, 0 corresponds to this point at the coordinates 2, 0, or in other words, the orange dot. And the output of that, the thing that gets transformed to, is 1 square root of 3. So right above 1, right about 1.7, or the square root of 3, is the output for that vector 2, 0. Now, the use of color and kind of helps us to see which points go with which. And you can imagine that what this is doing, what this linear transformation, or sorry, this matrix transformation does, is it rotates the points in R2. For some reason, these numbers, 1/2 minus square root of 3 over 2, square root of 3 over 2, and 1/2, have the action of rotating everything by about 60 degrees, it looks like. Now, in the next video, we're going to talk about what the entries of the matrix actually correspond to. It will be a little bit clearer how the matrix is connected to the action. But for right now, some matrix transformations look like rotations of the point in R2. Now, we've called it a linear transformation here. We'll explain why that is. But for right now, it's definitely a matrix transformation corresponding to a rotation. As another example, let's take the matrix -1, 0, 0, 1 to be our matrix involved in this matrix transformation. Let's choose as an input -3, 1, and if we multiply this matrix onto the vector -3, 1, we'll get out +3, 1. Now, what does this look like if we were to draw a picture? Well, let's do the following. Let's actually take a picture. Again, the same thing is true here. Our domain is R2, so all of these points here in R2, no matter where they lie in relation to the axes, are going to be mapped by multiplication of this matrix on and then spit out here. Now, actually, because this is a photo, we can kind of tell what the features look like. So if we were to take a look at -3, 1, oh, that might be, perhaps here at the top of the toddler's tongue. And the action of that spits out +3, 1. And you can see the top of the tongue actually got mapped to there. Now, we've done that action for every single point in the photo. And it looks, for all the world, like this matrix transformation is a reflection across the y-axis of the points in R2. All right. So these images that we'll see in the next couple of slides come from Interactive Linear Algebra by Dan Margalit and Joseph Rabinoff. And you can find that text at math.libretext.org. And we're grateful for the use of these photos. So to take another example, if we have 1.5 on the diagonal of this matrix, and we use that to define our matrix transformation, plugging in 1, 2 would give us 1.53. And in particular, if we see what that looks like for another picture, 1, 2 might correspond to this baby's eye. And as you keep track of where that eye happens, 1.5 and 3 is just a little bit farther up from the origin. And actually, what happens is that every point is spread out a little bit farther from the origin. The picture looks like we've zoomed in on the photo, or we've enlarged it, scaled it. So some matrix transformations correspond to very natural actions you might do in a photo editor of enlarging your photo. Next, if we take the matrix 1, 1, 0, 1 and use that for our matrix transformation, plugging in, for example, you should check that 1, 3 maps to 4, 3. What's going to happen here is we're going to take a photo, and the x and the y coordinates are going to be used together to determine what the top coordinate is. The bottom coordinate stays the same, it turns out. And so what this looks like is what we call a shear transformation. We're kind of slanting the points in a certain way, or we're shearing them. And so if you have a picture of a sheep, what do you call this thing on the right? Well, that is a sheared sheep, of course. And that is one of the best and oldest jokes in linear algebra. Okay, now with those examples, we've kind of illustrated that matrix transformations can actually imitate some of the actions you might do in a photo editor. They can be very useful, very practical tools to understand certain actions that pop up normally in natural life. Now, one of the things that is helpful, one of the things that makes this all work, are these properties shown here. Now, when you multiply a matrix A onto a sum of two vectors, now that's of course a matrix transformation of u plus v, it turns out that that's the same as A times u plus A times v. Or in other words, the matrix multiplication onto vectors distributes over those vectors. Now, it's also true that if you were to scale your vector before applying the matrix transformation, you'd get the same thing if you did the matrix transformation first and then scaled afterwards. Or in other words, you could say that algebraically by saying we can factor a scalar outside of this matrix vector product. Now, this works for any pair of vectors u and v and for any scalar. And these are properties that may not be surprising to you. They kind of resemble the distributive law and factoring out that you've been doing for many years. What's new here is that we're talking about matrix vector multiplication. And so this will be helpful. It may not look so significant right now, but just wait a second. And here we go. we have our definition of the course. It's going to be a very important one. We're going to talk about what a linear transformation is. So a function or mapping or transformation T is called a linear transformation if it satisfies these two properties, which may look kind of familiar to you, but let's see what they say. We're saying that if T, the function, is applied to the vector u plus v, it equals the same thing as if you had applied T to u and applied T to v separately and added them together afterwards. So it's not exactly the distributive property because this isn't multiplication, but it looks an awful lot like that distributive property. We can take T of each piece individually whenever we're adding vectors. Second, you can, again, it's not the same as factoring, but it looks like it. We're taking T of Cu, so a scaled vector in T, and whatever that scaling coefficient is, we can factor that out outside and multiply that onto T of u, and if it's linear transformation, those two things should be equal to each other. Okay, now, comparing that to the previous screen, the two properties look an awful lot alike, but here we were talking about matrix transformations, and here we're talking about linear transformations. So what can we say? Well, we can say that if T is a matrix transformation, if T has that matrix times vector form, then T is automatically a linear transformation, just because the multiplication properties satisfy these rules. So that means that every matrix linear transformation is a linear transformation. Now, what's interesting in the next video, part C, we're going to see that actually vice versa is true too, that every linear transformation can be thought of as a matrix transformation if you think about it in the right way. So we have that to look forward to. But moving on to a second comment. Not every linear transformation shows up written as a matrix transformation. So we'll show that actually you can write it as a matrix transformation, but that may not be how it originally is presented to us. So as a couple of examples, let's start by taking a look at a map. This is not a matrix transformation because it just takes a vector and just spits out a vector, and the rule is that you use the entries of the vector and you use them to generate the entries of the output vector. So T of x1, x2 is going to be 3x1 minus 2x2 and then x1 plus x2. And we want to know, is this function a linear transformation? Well, how do we decide that? What we need to do is think about the definition. Our definition of linear transformation requires that if T be one, that T satisfies these two rules. So we're going to see if T of u plus v is equal to T of u plus T of v. Now, how do we do that if we don't have u and v specifically given to us? What we'll do is represent u and v generically. We'll just put u1, u2 for the entries of u, v1, v2 for the entries of v, and we're going to use this rule, and we're going to figure out what T of u plus v is, and T of u plus T of v is, and we'll see, is it true that the two sides are equal to each other? Okay, so let's take the first quantity of the left-hand side, T of u plus v. Now u and v, if we plug those entries in, we can actually simplify. U plus v, where u1, u2 plus v1, v2, is actually just the sum u1 plus v1, u2 plus v2, right? We're just doing vector addition inside there. Now what we're going to do is use this rule. We're going to think of x1 as corresponding to the top entry and x2 as corresponding to the bottom entry. And this tells us what T is supposed to do. T is supposed to take 3 times the top entry minus 2 times the bottom entry. So T of u1, v1, T of this vector should be 3 times u1 plus v1 minus 2 times u2 plus v2. And then the rule says that the bottom entry should just be the sum of the top and the bottom entries. So we'll have the sum u1 plus v1 plus u2 plus v2. That's what T does. when you have this specific vector plugged in. That's what t of u plus v is. And if we want to, we can simplify just a little bit by distributing the coefficients through. So we'll get 3 of u1 plus 3 of v1 minus 2u2 minus 2v2. And then we can erase the parentheses here and just write u1 plus v1 plus u2 plus v2. All of that is equal to t of u plus v. Now we want to know, is that equal to t of u plus t of v? So let's start by filling out what t of u plus t of v is. Remember what the rule t does. It uses the coordinates in these particular ways. So t of u1, u2 will be 3u1 minus 2u2, u1 plus u2, and v1, v2 will give us the similar looking vector for the answer there. Now we're adding these two vectors together. So if I were to just add straight across, we'll get 3u1 minus 2u2 plus 3v1 minus 2v2, u1 plus u2 plus v1 plus v2. Now the question is t of u equal to t of u plus t of v? Is this last entry on the previous row equal to this last entry on the second row? And as you compare the terms, there's 3u1 minus 2u2, 3v1 minus 2v2, u1, v1, u2, v2. They do show up. They show up in different orders, but because we're adding and subtracting, the order doesn't actually matter. Yes, these two things are equal to each other. So remember, that was the first thing we had to check. Is it true that t of u plus v is equal to t of u plus t of v? And the answer here is yes. We don't yet know it's a linear transformation, but we're off to a good start. Now we'll be able to finish by checking that second property. Is it always true that t of cu is equal to ct of u when u is a vector and c is a scalar? So let's again just write our generic u as u1, u2. We'll suppose that c is just some arbitrary scalar, and we'll try to compute the left-hand side and the right-hand side and see if they're equal to each other. T of cu looks like t of c times the vector, and we know that when you multiply a scalar onto a vector, it's the same thing as multiplying the scalar onto each of the entries. So we get c1 cu1 cu2 inside the function t. Now remember our rule for using the entries of the vector to generate the output. We're going to get 3cu1 minus 2cu2. Then we'll add cu1 plus cu2 for our second entry. Now again, simplifying just a little bit, we can get rid of the parentheses basically, and we get this expression for the left-hand side, t of cu. Now for the right-hand side, ct of u, things are a little bit different, but you can recognize them. We'll have c times t of u1, u2. We'll use the rule to see what t of u1, u2 should be, and then if we do that scalar multiplication afterwards, we'll end up with c times the first entry, c times the second entry, and distributing that c through, we'll get this expression here. Are these two quantities the same? And they are indeed, as you take a look at that. So since we've shown that both t of u plus v equals t of u plus t of v and t of cu equals c of t of u, we've checked both of the conditions for t to be a linear transformation, and it passes both of those conditions. So yes, t is a linear transformation. All right. Now as another example, suppose we had a function s. S is defined by s of x1, x2 is x1, x2. That's multiplication there. And then we've got the addition of x1 and x2 in the second entry. We want to know, is S a linear transformation? Now, as you compare this problem with the previous one, you might notice some differences that might look significant, or you might not think it's very significant, the differences here. So what we're going to do to answer this question is check those two conditions for being a linear transformation. Is it always true that when I apply S to u plus v, I get the same thing as distributing S onto both u and v? And we'll answer that as we just did. We'll compute the left-hand side, we'll compute the right-hand side, and see if they're equal to each other. So starting with S of u plus v, we'll plug in what we know for u and v. And I know that if I were to add those together, I would just add across. This tells me the rule for computing S of something. So u1 plus v1 times u2 plus v2, and then I've got the sum down below. And then, because it's multiplication here, if I were to simplify, I'm actually going to distribute through, and I'll end up with 4 added terms on the top, and 4 added terms as we'd expect on the bottom. Okay, that's S of u plus v. Taking a look at S of u plus S of v, here we're going to apply S to each of the vectors individually, and then add them together. And as I get the final answer there, we're going to compare. Is this second quantity equal to the first quantity? Is this vector equal to this vector? And as you take a look at them, the second entry on each looks like they do match up, but the first entry of the second one only includes part of the first entry from the first row. So unfortunately, no, these are not the same. They're not equal to each other. And because S fails this condition, we don't even have to check the second condition. We already know that this vector, this transformation is not a linear transformation. It doesn't satisfy both of the two conditions. Okay, so if you are asked a question on a homework assignment or otherwise to decide whether something is a linear transformation, you want to follow these basic steps. You want to check whether the addition property holds for the linear transformation. You want to check whether the factoring a scalar out of the linear transformation also holds. If it doesn't hold, then actually it's not a linear transformation. And hopefully we've done a decent job showing you how you might go about doing that. All right, now here's a problem that's a little bit different. If we know that T is a linear transformation, so that's given to us at the outset, and we're told that T of the specific vector 0, minus 1 is equal to the vector 2, 2, and T of 3, 3 is equal to T of minus 3, can we use this information to determine T of 3, 0? Now, as you take a look at this, neither of these vectors is T of 3, 0, and we're not really told what T is as a general rule. We're not told the formula for T. We're just given the input and output at two specific points. So how in the world would we use this to determine T of a third point? Well, what we'll do is go back to the problem and read carefully, and it tells us that T is a linear transformation. Now remember, that means that T of u plus v is equal to T of u plus T of v, and T of cu is equal to CTU for any vectors u and v and any scalar c. So how can we think about this? Can we use this first property in any way? And if I were to take a look at it, I know what T of 0, minus 1 is, and I know what T of 3, 3 is. So maybe I should use 0, minus 1 and 3, 3 as my vectors u and v. If I do that, plugging 0, minus 1 and 3, 3 in, on the right-hand side, I'll get T of 0, minus 1 plus T of 3, 3, because that's what the linear property says. And I know what T of 0, minus 1 is. It's 2, 2. And I know that T of 3, 3 is minus 1, 3, so I can add those vectors together, and I'll get it at 1, 5 as my answer. Now, on the other hand, adding 0, minus 1 to 3, 3 is going to give us the vector 3, 2. So this formula, using the u and v that we did, just tells us that T of 3, 2 is equal to 1, 5. And we actually want to know what T of 3, 0 is. This doesn't quite do it for us. But if you think about how you might combine these vectors in a different way to create 3, 0, well, remember the first vector has a 0 in the first, and it's got a minus 1 in the second entry. So anytime I add one of these vectors, I'm going to drop the second coordinate by 1 while leaving the first coordinate at 3, which seems like it could be useful. So in fact, what I might want to do, if I wanted to get T of 3, 0, I could take 3 times that first vector and add it to 3, 3. Now, how do I use the properties of a linear transformation to determine what this thing should be equal to? Well, remember from the first property, t distributes over addition. So we're going to take t of the first vector and add it to t of the second vector. And the good news for me is that t of 3, 3 is already known. That's minus 1, 3. But in the first expression there, I've got t of 3 times 0 minus 1. What I'm going to do now is use that second property of linear transformations. If I have a scalar multiple of a vector, what I can do is sort of write that scalar multiplication outside the function. So t of 3 times 0 minus 1 is the same thing as 3 times t of 0 minus 1. And that's good because I know what that is. T of 0 minus 1 is 2, 2. So I've basically got 3 times 2, 2 plus minus 1 times 3. Now doing that scaling and then adding those together gives me a vector that is our answer. 5, 9 is the value of t of 3, 0. Okay? Now, maybe from these two lines you get the idea that actually we can figure out what a lot of vectors are if we just kind of take 0 minus 1 and 3, 3 and write them in different combinations. Our properties of linear combinations allow us to move the function onto each piece that's added and factor out any scalars we run into, and that allows us to figure out, based on what we just know about these two input and output values, we can figure out many different output values for many different inputs. In fact, if you were to think about it, you might realize that this is actually enough information to figure out what t of any vector in R2 is. You might think about how you could justify that. All right, so as our last exercise for this video, this one is comes from your textbook. It's not assigned so far as I know, but it's kind of interesting from a theoretical standpoint. We're going to let u and v be linearly independent vectors in R3. So these are vectors in 3 dimensions, and let P be the plane through u, v, and 0. So remember, the span of two linearly independent vectors is a plane. The parametric equation of that plane P is given by x is equal to su plus tv, where s and t are free scalars. They're allowed to be anything at all in the real numbers, and as they do run through all possible real numbers, that's going to sweep out all the possible points in our plane. So our question here is to show that a linear transformation t from R3 to R3 is going to take that plane, and the points of that plane are going to be mapped onto a plane through 0, or a line through 0, or just the origin. So whenever you take the linear transformation of that plane, you're going to get a plane or a line or just a point. Now, how would you do that? We're not actually going to run through the full solution here. I would like to leave something for you to think about. But one thing we'll do is start with what we're told. We're told that t is a linear transformation. And so what do we know about linear transformations? Well, we have a couple properties that hold for linear transformations. And so what I'd like you to do is think about what would happen if you took t of x. T of su plus tv is going to be t of some point on the plane. And what does your linear transformation property tell you that this should equal? And how does that show that the image of a plane is either a plane or a line or just a point? Should be fun to think about. Well, we'll stop there. Our outcomes for this video are as shown here. Please take a second to review this list and make sure that you can do each of these things. If you have any questions, please let me know. Otherwise, I will see you in the next video.